right, that was quick. Now we're going to do trees are really good for representing equations. And in fact, when you write something in Java and they compile it, they use a context-free grammar to build a tree structure for it. So, and everybody see whether this is a good equation, what we're representing here? Right? We're kind of missing we need brackets, right? And how would you, what code would you do to evaluate this, right? Well, you're like always, you recurse on the left subtree and the right subtree, and they send you the evaluation of their tree, and then what you do is you multiply them, right? So you apply whatever operations at the root to the left value and the right value. The base case here needs to be not the empty tree, but an actual number. All right, so here's some code. So imagine the input f is a tree like this, but some of the leaves, instead of being real numbers, are the character x, y, or z, right? So then we're given such an f, and we're given a value for x, y, and z, and we don't want to modify f at all. We're just looking at it. But we want to plug those three values in for x, y, and z, and then evaluate. Right? Everybody get the problem? So how do you do it? Well, the base case is if f is just a real number, then you return that real number as the answer. And if f is the character x, then you return the value for x. Right? And if f is a y or a z, it's the same. But if our tree f is a bigger tree that has the root operation of plus, then you evaluate the left subtree using the same values x, y, and z, and you evaluate the right subtree, and you take their answers, add them together, and return it. Right? And if it's a minus, you do the same, except you minus, a times, you times, and a divide, you divide. Everybody kind of follow that code? Pretty straightforward. So here's a code that I got them to write up in 2011 last term. The input is, again, a same sort of function like we had before, and you take the derivative of it. And that gets the derivative. Everybody I know loves calculus. So here's the code to take the derivative. Right? We're given our function f, and we're given a variable x. And if f is simply the variable x, then the derivative of x with respect to x is 1. Right? So the answer is a tree structure that just is 1. Right? So if f is any real value or a single variable other than x, then you return 0, right? Because that's the derivative. Otherwise, now when we don't want to destroy f or have pointers into f, harvesting stuff out, cannibalizing it. We want our own derivative. So in order to get our own derivative, we will recursively copy the left subtree and recursively copy the right subtree, and then we'll recursively take the derivative of each. Right? And then now we can build the derivative. Right? So if our f looks like this, it's a plus with some big left and right tree, then what's our derivative? Right? The derivative is the sum of the derivative of g and the derivative of h. Right? Everybody buy that? And there's just a little example. If it's a product, then it's a little harder. It's the sum of g prime, the derivative of g times h plus g times the derivative of h. So you build that structure. Right? You build that little tree structure. And there's an example. And, oops, what's that little g doing down there? I just made these slides yesterday on the subway on the way home. So here, if it's a divide, then it's more complicated, right? We have g prime times h minus g times h prime, and then the whole thing is divided by h squared, right? And I got the menu up, thank you. And so here's just an example that g doesn't seem to be doing anything. All right, everybody good? All right, here's another problem, which is here I took the derivative of this, and because it has two divides, each of which are complicated, you get some big, scary answer out of that. And so then I asked, well, can I simplify this somehow? Right? Here we got 1 times x. Well, that should just be x, right? So wrote a little simplify program. Oh, in all of these programs, I got my first year I was teaching, my first year class was doing this, and you know they all hated me. Right? So here, right, how are we going to simplify this? So here's some simple code to simplify. All right? Suppose we have this big thing that we're simplifying. And you see that's a tree written sideways. It was written back in the days when you only could do typewriting. You couldn't put a guy anywhere. All right, so then what you do is if the function is just a real value or a single variable, then there's nothing to simplify, right? You just return a copy. We're copying what we return has to be a copy instead of destroying what we had. Right? Otherwise, we recursively simplify the left and the right. And then, once we do that, here we simplify the left and the right. We just locally at a root. Remember the rules is you're not allowed to go down into the left or the right. Right? I want this to be constant time at the top. So all I'm doing at the top are really simple things. Well, it's a little bit of a lie. I peer down into the left just enough to see, is it 1? And if it's 1, then I simplify it, right? And if it's 0 and a plus, I simplify it. If it was a 2 plus 6 plus 2, then I simplify it, right? I'm just kind of looking at the roots of my left and right child. So that's not too big of a cheat. A little cheat because you're going down there, but not that big of a cheat. Everybody buy that? And in this case, it simplifies a lot. All right, so another program I got that first year class to write is to output text like this. And that was really beyond what they were doing, even though I gave them big hints.